Industry 5.0 is coming. A survey on intelligent NextG wireless networks as technology enablers. Abstract. Industry 5.0 vision, a step toward the next industrial revolution and enhancement to Industry 4.0, envision the new goals of resilient, sustainable, and human-centric approaches in diverse emerging applications. Factories of the future. Digital society. The vision seeks to leverage human intelligence and creativity in nexus with intelligent, efficient, and reliable cognitive collaborating robots, cobot to achieve zero waste, zero defect, and mass customization-based manufacturing solutions. However, the vision requires the merging of cyber's physical world through utilizing Industry 5.0 technology enablers. Cognitive cobots, person-centric artificial intelligence, AI, cyber physical systems, digital twins, hyper-converged data storages and computing, communication infrastructure, and others. In this regard, the convergence of the emerging computational intelligence (CI) paradigm and next-generation wireless networks (NGWN) can fulfill the stringent communication and computational requirements of the technology enablers in the Industry 5.0 vision, which is the aim of this survey-based tutorial. In this article, we address this issue by reviewing and analyzing current emerging concepts and technologies, e.g., CI tools and frameworks, networks in box architecture, open radio access network, softwareized service architectures, potential enabling services, and others. Essential for designing the object of CI and GWN to fulfill the Industry 5.0 vision requirement. Finally, we provide a list of lessons learned from our detailed review research challenges, an open issue that should be addressed in CI and GWN to realize Industry 5.0. Index terms: Industry 5.0, computational intelligence, next-generation wireless networks, human robots, collaboration network, in box, factories of the futures, softwareized networks. Introduction: Intelligent, resilient, and reliable next-generation or NextG wireless networks (NGWN) are envisioned to form a technological enabler for meeting the diverse communication. Hansen are with the School of Electrical Engineering and Computer Science, SEECS, National University of Science and Technology, NUST, Pakistan. And computational requirement of the Industry 5.0 applications and services, which are based on the core element, resilience, sustainability, and human-centric industry. Resilience refers to the increase in industry production while reducing the disruption and times of crisis. The sustainability mainly addresses environmental factors, such as energy reduction and reuse of the available resources. The human-centric approach places the human interests and needs at the core of the production process, including personalization and machine interactions. Concerning the core elements of Industry 5.0, vital communication and computation paradigm components and their subdivision, NGWN, are illustrated in Figure 1. NextG wireless networks, NGWN, lately with the deployment of 5G networks. Broad spectrum of research is being carried out to envision next-generation wireless networks or 6G wireless systems, closely integrated the omnipresent AI into every aspect of networking systems to enable hyper-flexible, intelligent end-to-end networks architectures. Primary goals include AI-native services-oriented architecture that possesses the inherent feature of flexible and enhanced service-based architecture (SBA) to provide hybrid 6G services, high data transformation and computation networks, and support for knowledgeable and autonomous human-centric systems. In this regard, the CI integration can play a big part in realizing the 6G vision. Computational intelligence, CI paradigm provides intelligent communication, computation, and function storage capabilities to numerous applications by utilizing state-of-the-art computational algorithms, deep neural networks, fuzzy systems, evolution AI, and swarm hyperconverged computing infrastructure, HCI, e.g. cloud edge computing infrastructure, on-premise private data centers, public data lake, and enabling communication technologies, NG-IoT and IIoT cognitive GPS systems, B5G, 6G wireless systems. The International Data Corporation (IDC) estimated the global spending on AI will increase from the 85.3 billion US in 2021 to over 204 billion US in 2025. CI native NextG wireless networks, CI NGWN, a new concept of CI native NGWN, is emerging following the convergence of CI paradigms. SDN and NFV-enabled communication networks, coupled with software-like service architectures, microservice architectures, which can provide the powerful integrated solution to sustain the needs of Industry 5.0 vision. It enables full automated and intelligent networks, resource management, and operations to deploy dynamic networks functions and connection services, which provide high degree of flexibility in numerous demanding scenarios. Integrated networks softwareization, AI native service-based architecture, multi-tenancy and service orchestrations, self-sustainable zero-touch networks, ORAN architecture, GT implementation for human-machine interactions, and time-sensitive networks, TSN, Industry 5.0 and CI NGWN, the fifth industrial revolution, powered by enabled communication and computation technologies, pave the way for new opportunities for firms to create value for their customers. In this respect, CI NGWN unlock new business model opportunities for firms to create all factors, e.g. leading telecom and vertical industries, to collaborate toward realizing the economic impact that would give everyone involved a fair return on their investment. Furthermore, understanding customer needs, i.e. connectivity requirement, is a prerequisite to understanding successful value creation and capturing. Therefore, the real value of CI NGWN is defined by improving the manufacturing process in terms of their responsiveness to the demand, efficiency, capacity utilization, and product service customization and innovation requirement in Industry 5.0. In this sense, it requires the human and value-centric design CI NGWN through vertical technology joint design to enable the actual realization and adoption of Industry 5.0 goals. The rise of Industry 5.0 vision. Transition toward Industry 5.0 vision. The world is experiencing the fourth industrial revolution, or Industry 4.0. One of the future projects that the German government outlined in its 210 High-Tech Strategy 2020 action plan. The end goal was to enhance digitalization in smart production and bring automated control under the vision of mass production, like in the preceding three industrial revolutions. However, one of the key differences among different revolutions lies in utilizing the state-of-the-art enabling technologies of the respective ages illustrated in Figure 2, e.g. the introduction of diverse ICT technologies facilitates the migration from electronics-based Industry 3.0 to the vision of Industry 4.0. Hence, the digitalization revolution of Industry 4.0 reshaped today's industry by increasing the efficiency and intelligence in manufacturing and automated processes. Lately, academia and researchers have started to discuss the futuristic visions for the next industrial revolution of Industry 5.0, an evolution and logical continuation that complement the existing Industry 4.0 paradigm. Industry 5.0 visions. Industry 5.0 aims for mass customized production with zero waste, minimum cost, and maximum accuracy, while a critical component in Industry 4.0 was mass production with minimum wastage and enhanced efficiency. However, the Industry 5.0 concept is yet entirely to be evolved. For example, discusses the various definition and observations of leading industry researchers and practitioners regarding the Industry 5.0 vision. All relevant Industry 5.0 concepts emphasize human and robot working in harmony to create an intelligent society. Robot working in harmony to create an intelligent society, where humans perform the creative task of innovation while robots carry out the rest. In this regard, the European Commission coined the futuristic blueprint to add resiliency, human-centering, and sustainable approaches to the Industry 5.0 vision. It enables people empowerment, workforce digital society in nexus with the goals of massive customization in optimized supply chains, easy adaptability, and scalable product varieties, bringing positive impact and benefits for different fields of society and realizing the next industrial revolution. Why Industry 5.0? The industry of the future needs to play functional part of equipping solutions to imminent societal challenges, preserving environmental and natural resources and climate change sustainability. Circular production model, emerging enabling ICT technologies, and revision of policies for energy consumption for efficient utilization of natural resources in the event of external shocks, e.g. COVID pandemic resiliency and digital hyperconnectivity and evolving digital skills for people empowerment and social stability, human-centric value. It is imperative for Industry 5.0 vision component to realize and enable the 70 goals of the Sustainable Development Goals, SDG, or global goals outlined in Agenda 2013 of the United Nations, UN, building blocks Industry 5.0. In the face of imminent societal challenges, FOF Industry 5.0 can provide innovative solutions via integration of current and emerging technologies and techniques. Notably, there have been significant advancements in various emerging technologies, robotics, IIoT, computer vision, big data analytics, and computation technologies, B5G wireless networks, and artificial intelligence, AI, which enable the new vertical and horizontal industrial applications. Some promising example applications of upcoming challenging trends are cloud manufacturing, the deployment of artificial, virtual, and extended reality, AR, VR, XR, in mesh-connected digital twins, DT, of the factory. Supply chain management, DT, enables cobot, automated guide vehicles, AGVs, predictive maintenance, intelligent healthcare, and smart education. It is not long before humans will start interacting closely with AI, and DT enables the cobot systems and machines inside the FOF. Additionally, Industry 5.0 brings the other critical features to the existing Industry 4.0 paradigm, for example, matrix production based on grid layout, categorized and standard the manufacturing cells, combines the concept of cell manufacturing, lean productions, cell neutral and smart wireless networks, multi-board systems, and AGV. It enables hyper-customized and discard the monolithic rigid production by decoupling the warehouse logistics and manufacturing floor production and using the control software to connect multiple manufacturing cells in matrix grids for sustainable, flexible, resilient, and customized productions flow by using individual configurable load handling attachment. These autonomously navigating HV can easily pick up and transport different workpiece or tools from warehouse. Similarly, other enhanced features also exist. Zero defect and smart additive manufacturing, monitoring and predictive maintenance, human-robot collaborative manufacturing, renewable energy resources, and green industries. A. Research methodology, motivation, and contributions. This subsection discusses the SCREAM method we adopt, motivations, and the contributions of our paper, followed by each organization. Research SCREAM methodology. The method for selecting the most relevant and authentic literature is summarized in Table 2. For publication screening process to be reliable, the screening process was repeated through three separated independent campaigns. Our findings are compiled from 2022 for selected search strings, Table 2. Prior to final processing, it is essential to establish whether the compiled data is relevant to an area of interest, i.e., to determine whether it is based on the paper's abstract, instruction, and conclusions. The search database contains a number of articles with a key digital or twin in the title of the abstract, which is not intended to refer to the digital twin and virtual image of the process as a whole. Similarly, we encountered the same situation while searching for industrial IoT, zero defect manufacturing, computational intelligence, Industry 5.0, and other relevant data. We applied the detailed pre-processing check based on screening procedures and excluded articles of this sort from the final database of literature for our survey paper. Our motivation, Industry 5.0 and CI and GWN have already become critical topics in academia and industry. We read through all the incorporated papers in our collected literature database, obtained through the aforementioned screening methodology, literature review and limitations. Many research works are published on Industry 5.0, CI, and GWN vision, enabling technologies, possible applications, and use cases. In this regard, we categorized and summarized some of the available literature and reviewing works in Table 3. Based on critical enable features, CI and GWN and each compliance with the Industry 5.0 vision, we try to find the common ground and proportions towards the Nexus Industry 5.0 and CI and GWNs, especially how CI and GWN can act as a technology enabler for realizing the Industry 5.0 vision. From Table 3, it is observed that all authors have explored Industry 5.0 with a different perspective, for which we gave the summarized remarks and remarks the nature of discussion in reviewed literature on the basis of covering the CI and GWN feature coverage, i.e. high coverage, medium coverage, low coverage, and unavailable. For literature review content, it has been revealed that there has been limitation of less coverage of the Industry 5.0 vision concerning numerous features of CI and NextG wireless networks, i.e. ORAN, softwareized NIVs, service provisioning, cloud edge native computing networks, architecture, and others. For example, Naya et al. And in 58 and respectively, reviewed the various features relevant to some of CI techniques and applications in 60 vision, while Sharadi et al. In 51 has addressed the human-centric features in futuristic 60s. Similarly, fewer attempts have been made to identify and cover the KPIs of the three pillars of Industry 5.0 vision, i.e. sustainability, resilience, and human-centric, and how various critical features of CI and WGN can meet the KPI requirement. Based on the factor mentioned above, CI and WGN is expected to open up novel opportunities for Industry 5.0 research and development as critical technologies enabler in the foreseeable future. Our contributions, as can be seen from Table 3, this is the first attempt to survey the path toward Industry 5.0 comprehensively, while considering a broad range of CI and WGN elements. Hence, the impact of this study lies in following key contributions: technology enablers and requirements. An important requirement of the technology enablers concerning the Industry 5.0 vision is identified and discussed in this paper. CI, NGWN, and NIBs, the design objective, vision, and NIB architecture. CI, NGWN has been categorized and discussed to meet the diverse KPI of the technological enablers in Industry 5.0. Multi-tenant softwareization architecture, or industry automation and control software frameworks that allows customized and intelligent services to provide for Industry 5.0 application has been described and explored in the paper in light of the technological transition in industry automation, open and intelligent land. This paper discusses and shapes the ORAN and private networks for Industry 5.0, CI in the Industry 5.0. In Industry 5.0 framework, sustainable, human-centric, and resilient features are explored and discussed as result of the combination of CI and cloud fog edge computing network features, potential enabling services. The paper explores and discusses the potential enabling services for Industry 5.0, including DT as a service, NFV as a service, tracking as a service, AI as a service, and others. Summarize ongoing projects and demos. Lastly, project currently underway and completed publications, demos, and collaborations related to Industry 5.0 are discussed. Lessons learned and research challenges. Lessons learned from the reviewing research recommendations and the roadmap for future research challenges were presented to the community based on the reviewing research. Paper organization. The rest of the article is organized as follows. Section 3 gives an overview of the critical requirement incurred by the technology enablers of Industry 5.0 vision and the NIB architecture of CI and GWN, followed by Section 5 that discusses the role of requirement of CI techniques toward Industry 5.0. Section 5 discusses the virtualization in LAN of NGWN, which brings the new futuristic opportunities for Industry 5.0 applications. Similarly, Section 4 provides a discussion on multi-tenant softwareization, the service provisioning for Industry 5.0 applications, which enables the customizable new potential services which are covered in Section 6. Section 6 covered the ongoing research works, project, and demo relevant to Industry 5.0. Finally, Section 4 covers the lesson learned and recommendations, research challenges, and the future opportunities, and Section X gives concluding remarks. Technological enablers of Industry 5.0 vision and how CI, NGWN, KPI supported IT. The automation and or expansion of existing Industry 4.0 application requirement, extending coverage, enhanced features, and new vertical and advanced applications in Industry 5.0 includes enhanced communication and computation service requirements. In this section, we first discuss the critical technology enablers to realize the Industry 5.0 vision section, followed by the enhanced KPIs, CI, and GWNs that can facilitate the requirements, technological enablers needed for the Industry 5.0 vision. Required technological enablers. The Industry 5.0 enabling technologies are multiple complex systems resulting from seamless coverage of emerging technologies and paradigms that bind physical and cyberspace to realize the vision. The successful working symbolic relationship between multiple complex systems and supporting technological frameworks in tandem can only enable the true multi-dimensional potential of the Industry 5.0 features. These Industry 5.0 technological enablers are human-machine interactions. Human-machine interaction technologies can enable the hyper-connectivity between machine and human to provide human-centric innovation, solutions, intelligence, cognitive and effective computing digital assistance, visual insight, smart management and control. Following enabling technologies support human-centric value design in Industry 5.0, cognitive and cyber-physical social systems, CCPSS, is rapidly growing interdisciplinary technology that combines cognitive computing architecture at the nexus of three critical spaces of machine cobots to deliver intelligent solutions. These three crucial cobots spaces are cyber, physical, and counterpart social human component for enabling human-machine interactions. By interacting machine learning and artificial intelligence with brain-inspired effective computing designs, CCPSS uniquely combines the best of the world through human intelligence to aid Industry 5.0 vision. Autonomous mobile robots, AMR, by combining AMR with HVs. Multi-directional production lines can be laid out instead of linear layout possible with conventional conveyors. Understand the surrounding environment in matrix productions. In the plant and between the warehouse and loading bayers, AMR ensure the movement of components inside among work cells. Several of the framework provide a quick overview of the concept of Industry 5.0 as well as broad vision, definition, technological enablers, and main goals. Processing tasks related to AMR including collision, avoidance, and visual navigations are migrated to the on-premise cloud edge. Augmented reality technologies, integrated virtual information with the real world to provide computational generated perceptual information. AR, VR, XR. The technological use include multimedia 3D modeling, real-time intelligent interactions, sensing visual insight, and more. Cognitive service provisioning. Cognitive service provisioning provide a customized standalone services to meet the service demand of previously discussed human-centric applications, such as tracking technologies, real-time monitoring industrial workforce, navigational support AMR, multilingual support for natural language processing (NLP) applications, CV for human cognitive abilities is gesture recognition, pattern recognition, and cognitive APIs, CCPSS-based cobots, real-time virtual simulation, and digital twin. Digital twin technology implementation enables the real-time cyber world through creating of virtual digital images of counterpart physical assets, which can be devices, process, sensors, etc. DT technology realizing following critical two function aspects, DT of physical assets and process optimization by bridging the physical and cyber worlds. DT models the entire complex system comprised of deployed industrial assets, enable them to communicate and interact intelligently to take action and optimize the multi-fold value of the output production process. Together with IIoT and CPS, DT can facilitate this true digital hyperconnectivity (FOF) if allowed. The remote maintenance and predictive maintenance paradigm inside the factory ecosystems is similarly massive interconnected DT systems integrated with augmented technologies can effectively utilize human intelligence for management and control purposes.